All right, well, our first chapter is chapter 1, and chapter 1 is over matter and measurement. Before we get started on chapter 1, I want to switch over to my document camera. And my document camera here, I've got a document which is, it's the in-class assignment. In the folder where you found this video, you will also find the PowerPoint presentation that you can look at any time. And then you will also be able to find this document, which is the in-class assignment. And then you may find some other documents in there that are helpful. Now, in the main folder with all of the lectures and stuff, you will also find a copy of the periodic table of the elements. And here we've got a custom-made copy of the periodic table of the elements. We will talk about these a little bit later. We'll talk about how this is set up and what it is. There's a key up here and everything, and it's color-coded for your convenience. So we'll talk about what those numbers mean and everything. I recommend printing out a copy of that. If you've got a color printer, that will be quite handy. In addition to that, on the back of the periodic table, it's actually a separate document on eCampus, but when I print them out for the testing center, we've got them like this. So here we've got fundamental constants, which are going to include a lot of important fundamental constants, just so all scientists agree that these are the values for those numbers. And those will be quite useful as we go through this, this class and the second half of general chemistry as well. In addition to that, we've got useful conversion factors, and those useful conversion factors, we will be using some of these in this chapter, but we will use most of these throughout the course of the semester. So you'll want to get that all printed out and have that ready to go. Well, I'm going to go back to the presentation, and so we'll start with chapter 1. And here we've got this first one, very basic. It just talks about what chemistry is, the study of matter, and the changes that matter undergoes. And we will find that matter is anything that has mass and takes up space. Now, I'm not going to go into this in any great detail, but this is a lot of stuff. Matter, you know, the study of matter and changes that it undergoes, well, there's a lot of things you can study. And so chemistry is a very broad field of science. And it overlaps substantially with both physics and biology. And you will find that you want to be well versed in a basic chemistry in order to be knowledgeable about those other things. So this is the first class in a series of college classes that you would need to take to progress on and become experts at chemistry. So what matter is, the basic building block of matter is atoms. So atoms are the smallest unit of matter, sort of. It's the smallest unit of an element. So it's the basic building block that we will look at. We will find in the next chapter, and you probably know this already, but atoms are made up of smaller particles called electrons, neutrons, and protons. And that if you dig further into physics, you will find that those protons and neutrons are actually made up of even smaller particles. We are going to talk about the electrons, protons, and neutrons, but for now, we will say that atoms are our basic building blocks. There's 3 different types of atoms on this figure over here on the left. There's hydrogen, which are white, the red ones are oxygen, and the black ones are carbon. Those are 3 different elements. All right, so those are 3 different elements. And so all of the elements of the same kind are alike. We will find, or all the atoms of the same kind are alike, mostly. All right, and you'll see up here that we've got several different substances. If you've got a compound is made up of more than one type of atom, more than one type of element. And you'll find that most of these things here are compounds with the exception of oxygen. The oxygen you breathe is O2. So when you take a deep breath of air, 21% of that air is oxygen molecules, and you need to have those to survive. These other ones we need in various other amounts to survive. Well, water, of course, we need to have that. Carbon dioxide is a product of respiration, and it's also used in photosynthesis. So it's a key component of the carbon cycle. Ethanol is when you ferment sugars, it becomes one of the products is ethanol, and we, of course, can use that for fuel, or we can use it for something like an alcoholic beverage. Proceed cautiously with that. Ethylene glycol, that is the substance that is in antifreeze, and you'll see it has an extra oxygen in it compared to ethanol. Well, that one extra oxygen changes the properties of that molecule pretty substantially. So we will look at that. And then, of course, here is aspirin. Aspirin can help you with things like pain and headaches. So next, we're going to look at the different states of matter. There are three primary states of matter that we will refer to: gas, liquid, and solid. Gas is the most disordered, the most spread out. There are large empty spaces in between the molecules. That means that you can compress gas molecules. You can compress gases into a smaller sample. If you take 1 liter of a gas, you can compress it into half a liter or even to 1/10 of a liter. And you won't be able to do that with these other substances, with these other states. All right, because the molecules are moving around freely, we'll find that they take the shape of whatever container they have. So they do not have a fixed volume and they do not have a fixed shape. Liquids, on the other hand, they do move around quite a bit, but you'll find that the spaces in between the liquid molecules is going to be pretty small. They are essentially bumping into each other, whereas in a gas, the molecules are barely ever touching each other. In a liquid, they are constantly bumping into each other, and there's just not much space in between them. And as a consequence, we will find that they have essentially a fixed volume. If you take 1 liter of water, for example, and you try to compress it, you'll find that it's not very compressible. You won't be able to squeeze it down into a smaller volume, at least under normal conditions. All right, but it doesn't have a fixed shape. The water will take the shape of whatever container happens to be available. Solids, on the other hand, have a fixed shape and a fixed volume. The molecules are not free to move around in any direction that they want, and as a consequence, solids tend to have a fixed shape. So we want to go over to the in-class assignment number 1 on chapter 1, and we'll go over to my document camera here. And we'll just go through each of these. So for each of the following substances, indicate whether or not it has each of the properties listed. Assumes the shape of its container. Well, we know things that assume the shape of their container are going to be gases and liquids. So solids, no, does not assume the shape of its container. But liquids, yes, will assume the shape. And gases will also assume the shape of their container. Next, we've got, is it compressible? That means, can we take 1 liter of it and compress it down to a smaller volume? And the only one that's going to be compressible is going to be gases. So H2O gas, yes, will be compressible, but these other two will not be compressible. Next, will it expand to fill its container? Okay, well, this one is going to be similar to the previous one, because the only thing that will expand to fill its container is going to be a gas. So yes, the gas will expand to fill its container, but H2O solid and H2O liquid, no, will not expand to fill their container. And then finally, has a fixed volume. And so has a fixed volume. So solids, yes, have a fixed volume, as do liquids. And we will find that gases, no, do not have a fixed volume. So I will say that not all of the problems that we're going to be doing this semester are this easy. This one was an unusually easy problem. They do get harder. All right, so the next thing we want to look at are the different elements. And I want you to have a working knowledge of the names of the elements and the symbols that go with them. And so I've picked out 60 different elements where if I give you the symbol, I want you to be able to give me the name. And if I give you the name, I want you to be able to give me the symbol. Many of these you already know, but some of them you may not be familiar with, and you may need to study that a little bit. So keep that in mind as you are studying this. So we'll start here with H. Of course, H, you know that one is helium. And in fact, it's not helium, it is hydrogen. Yeah, so H is hydrogen. He, of course, is helium. You will find that this first page, you probably know all of these. Maybe you're not sure about Be, but I bet you know most of these. So He is helium. Li, of course, is lithium. Be is beryllium, and that's an interesting element. B is boron. C, of course, is carbon. Almost certainly you knew that. N is nitrogen. O is oxygen. F is fluorine. And element number 10, Ne, is neon. Now, the only interesting thing here I want to point out about fluorine is that fluorine, it's spelled Fluorine, not Flour. And so it's not fluorine, it's fluorine. And fluorine, we're going to talk a lot about fluorine over the course of this semester. I like to call it the most reactive, meanest, baddest, most electronegative element on the whole periodic table. If you are exposed to elemental fluorine, you are going to have a bad day. And so fluorine is pretty bad stuff by itself. So if you look right there in the name, it has Flu, it has the word flu in it. And flu, of course, is pretty bad stuff as well. So that's one way you can help to remember how to spell fluorine. Now, when it comes to test, I'm not going to test you on the correct spelling of fluorine, but it's something that you might care to know. All right, for our next 10 elements, pretty good chance that you know most of these. Maybe not all of them, but you probably know most of them. Na, this one is very commonly used. Sodium, so we use sodium quite a bit in the form of sodium chloride. Mg, I bet you know that one, is magnesium. Al, this is the most abundant element, or most abundant metal in the Earth's crust, and that is aluminum. If you grew up speaking British English, you probably know this as aluminium. And if you spell it that way, that's fine by me. So aluminum, aluminium, it's one of those weird differences between British English and American English. Si, this is silicon, very common, very abundant element in the Earth's crust. P is phosphorus, important biological element. S is sulfur. Again, there is a different British spelling for that. They have a PH in place of that F, but again, not a big deal. Chlorine for this one. So chlorine, when sodium and chlorine come together, they'll make sodium chloride. So we'll talk about that chemical reaction at a later point in the semester. Element 18, Ar, this one is a gas, and it is called argon. And argon makes up a little bit less than 1% of the Earth's atmosphere. But scientists didn't discover it. They weren't able to identify it until about 125 years ago. Next element, K, is potassium. Ca is calcium. All right, you probably knew those. So we'll look at the next 10 here. On this, there may be a couple of these that you aren't quite familiar with. No big deal. SC is scandium. Scandium has quite a few properties that are similar to aluminum. Ti is titanium. It's a very strong metal. It's used for a lot of different applications. V is vanadium. It's used in making stainless steel less reactive. Cr is chromium, also used in stainless steel quite a bit. Mn is interesting. That one is called manganese, and it looks kind of like magnesium, and sometimes people get manganese and magnesium mixed up. And in fact, the name of manganese came from a mixed up spelling of the word magnetic, and so it's one of those weird etymologies for the name manganese. If we go to the next one, Fe, you probably know that one. That is iron. And you will see that this is one of those ones where the symbol doesn't seem to match the English name for it. And that's because the symbol is based on the Latin name. And the Latin name is ferrum. Next one is Co, or cobalt. Ni, this one's pretty easy. That is nickel. Cu, this was a pretty abundant, or pretty common element. We use it quite a bit for coins. It is copper. And then our last one here on this one is Zn, and that is zinc. So on these next 10, there's a pretty good chance that you don't know one or two of these. And again, that's okay. If you knew everything, why would you take the class, right? So element 31, this one wasn't discovered until, about 120, 130 years ago. It is called gallium. Maybe more than 100, maybe like 150 years ago. The next one is Ge. It is called germanium. And the next one after that is As, and it is called arsenic. It is called arsenic. And if you were arsenic is it's used as a poison for like rat poison and things like that. So you probably have heard of arsenic. Se is called selenium. Br is called bromine. Kr is called krypton, kind of like the planet Superman was born on. Rb is rubidium. Sr is the element strontium. Y is the element yttrium. So that one is kind of a cool one. Zr is zirconium. You probably have heard of cubic zirconium as a fake diamond, costume jewelry diamond. So, all right, on these next ones, I bet you know a couple of these, but you may not know all of them. Nb is niobium, named after the Greek mythological figure Niobe. Mo is called molybdenum, my favorite element to pronounce, molybdenum. Tc is called technetium, and it is not a naturally occurring element. It turns out that all the isotopes of technetium are radioactive, and so it does not occur in nature. It just doesn't show up in any significant amount in the Earth's crust. Next one is ruthenium. All right, rhodium. PD you probably have heard of. It is palladium. Ag is a common semi-precious metal, silver. CD is a heavy metal. It is cadmium. In is it is called indium, and then the next one, Sn. The Sn comes from the Latin name stannum, but the English name for this is tin. So, all right. So for our next 10 of these, we're going to look at not all of the elements, but we're going to look at 10 more, and you'll see that these are all not sequential. We've skipped a few here. I is iodine, which is important for good thyroid health, which is why I put that one there. Ba is barium. It's a heavy metal, so I put that one on there. W, the German name for this is wolfram, which is where we get the W, but in English we call it tungsten. Pt is a precious metal, platinum. AU, element 79, is another precious metal, gold. You probably knew that one. Hg is a heavy metal, quite poisonous. That is mercury. Pb, which is named, again, the Latin name is plumbum, but we call it lead in English, another heavy metal. Rn is a radioactive gas that we call radon, and it turns out to have some important health issues. And then these last two, this one is uranium and plutonium. So uranium and plutonium. And those are both radioactive materials that are used in nuclear power. We want to classify matter into different categories. And so there's 4 different categories that I'm going to list here. And those 4 categories are homogeneous mixture, heterogeneous mixture, pure element, and pure compound. And there's a little flow chart here that is from your textbook. Matter, is it uniform throughout? Well, if it is, then it's going to be something that is homogeneous. If it is not, then it's going to be heterogeneous. If you can see different parts of of whatever your sample is, then it's probably heterogeneous. So if you look at something and you can see the different parts of it that are different substances, then it's probably heterogeneous. And it turns out heterogeneous makes up a good portion of everything. Heterogeneous mixtures are quite important. But we have homogeneous, and that's going to include the homogeneous mixture, which we call a solution. We have pure elements and pure compounds. So if it had variable composition, that means if there's more than one substance in there, then we call that a solution. If there's only one substance, we would call that a pure substance. And we can break that down into, well, if it's a pure substance, is it an element, which means it only has one type of atom in there, one atom of one element, or is it a compound, meaning it has 2 or more elements in there. So that is compound. So when it comes to compounds, and an example of compounds would be water, water H2O, which you're quite familiar with. You can break down water into hydrogen and oxygen. If you put an electrolyte into the water and run electricity through it, you can get oxygen and hydrogen. We actually do this during the 2nd semester of general chemistry. And one of the things that we will find about compounds is that they always have a fixed ratio of one element to another element in that compound. And so a pure compound has the same composition regardless of where you get it. For example, water is always H2O, and if you break it down into hydrogen and oxygen, you will find that you will get a ratio of 8 grams of oxygen for every 1 gram of hydrogen. And it doesn't matter whether you get it from a river, a lake, from the ocean, it's always going to have that same composition. Another example is sodium chloride, just regular table salt. It has 1.54 grams of chlorine for every 1 gram of sodium that is present. All right. We're going to talk about the law of definite proportions more in Chapter 2 when we talk about Dalton's atomic theory. When we look at mixtures, we really just want to tell, is it a homogeneous mixture or a heterogeneous mixture? Heterogeneous mixtures means that it has more than one it has a varied composition throughout. For example, if you look at this chunk of granite here, you will see that there is a brown part of it, and then there is a black part of it, and sometimes you'll see little white bits of it, but you will see different parts of that mixture. And with the different parts of that mixture, that means that there is a different chemical composition of the dark parts versus the light parts. And so that is definitely heterogeneous. Homogeneous mixtures have the same composition throughout. They have different components, but they will have the same ratio of those components. And an example of that would be salt water. If you have salt water, if you take a little bit of salt and dissolve it in water, you will find that you have the same concentration of salt up at the top of the glass versus the middle of the glass versus the bottom of the glass. It should have the same amount of salt. And so we also refer to homogeneous mixtures as solutions. So uniform throughout, that is a homogeneous mixture. Over here, we've got the compound. This one is copper sulfate. It's actually the hexahydrate, so pentahydrate. So copper sulfate pentahydrate, and it's this bright blue compound. And if you take it and dissolve it in water, you will get a uniform mixture of that copper sulfate in water. And so you'll have the same concentration of copper sulfate up at the top as you do in the middle as you do at the bottom. And so that is homogeneous. All right, so we want to look at heterogeneous versus homogeneous versus pure compound versus pure element. And we want to determine which do each of these fall into. So first, what I'm going to recommend here is before I go through these, why don't you try to do them? So like pause the video for a minute and try to go through them and do them yourself. Okay, now that you've had a chance to pause that video and go through them yourself, let's go through them. Air, well, since air is made up of, about, let's see, 78% nitrogen, 21% oxygen, a little bit less than 1% argon, some water vapor, and some carbon dioxide, and some various other things in low concentrations. But we'll find that it's pretty uniform throughout, and so we will find that as a homogeneous mixture. Now, we are neglecting the fact that air has all kinds of dust in it. If we count the dust, it would be heterogeneous, but we're going to stick with air. We're going to say it's homogeneous. All right, distilled water. The distilled is to reinforce that when we distill the water, we should get pure water, and water we know is a compound, so this would be a pure compound. Next, we have nitrogen. If it's one of our listed elements on our periodic table, then we're going to say that it is a pure element. So if we had just regular, a pure sample of nitrogen, we would count that as a pure element. Salt water is a combination of salt and water, and salt dissolves in water and is evenly distributed, so that is going to be a homogeneous mixture. Oil and water, if you've ever taken salad dressing, you mix oil and like vinegar together, or you do oil and water, you shake it up, and the oil droplets will disperse through the water, but then they will settle to the top because the oil is less dense than the water, and so you'll get an oil layer and a water layer. You will find that is definitely a heterogeneous mixture. Next, we've got argon. Argon is one of our elements, so we're going to call that a pure element. Granite. Granite is just a type of rock. In fact, that picture I showed you on the previous page is granite. And so it is a heterogeneous mixture. Again, if you can see the different domains of substances where there's different colors, it's probably heterogeneous. And I say probably, there are some exceptions to that. Pizza, I just like throwing this one in there. Pretty much any food that you're going to have is going to be a heterogeneous mixture. All the interesting foods are heterogeneous mixtures. If you have a homogeneous mixture, it's not really a food. It's probably a beverage. All right. And even most of our beverages are heterogeneous. So next, we want to look at the different properties of matter. And we're going to start with physical properties versus chemical properties. Physical properties are properties that can be observed without changing a substance into another substance. So the mere act of observing the property doesn't change it into something else. A chemical property, on the other hand, to make the observation of that chemical property, you're going to have to do a chemical reaction. So the substance will be converted from one thing into another thing. And I find that the best way to demonstrate this is to go through and look at problem 1.2 on your in-class assignment. All right. And I definitely recommend going through these and attempting them yourself before I go through them. So you might want to pause the video and do that. All right. So the density of aluminum is 2.70 grams per cubic centimeter. Well, we haven't talked about density yet, but density is something where if you measure the mass and you measure the volume of a substance, then you can calculate its density. Well, in order to do that, you don't need to change it from one substance to another. If it's still aluminum when you're done making the measurement, then that's a physical property. So we're going to call that physical. All right, sodium reacts violently with water. Well, if it's reacting with water, then that means we're going to have a chemical reaction occurring. So that is a chemical property. The fact that it reacts violently, that is a chemical property. All right, the melting point of gallium is 29.8 degrees Celsius. So if we measure that melting point, we will find that we still have gallium when we're done. And so since it didn't change into a different substance, we're going to call that a physical property. So we will put physical. Next, the decomposition point of sucrose is 186 degrees Celsius. If you've ever cooked with sugar, just regular table sugar is sucrose. If you've ever cooked with it, when it gets to a high enough temperature, sugar starts to undergo changes. You'll get decomposition that will start to occur. If that goes unchecked, if you just heat it up and you don't pay attention to it, then it's going to burn. You'll get charred black stuff. So it starts to decompose and you'll get some carbon black. But if you decompose it just a little bit, you'll get some interesting stuff like caramelized sugar, which, oh my gosh, that's so good in cookies. Anyway, since it's decomposition, it's changing into another substance. That is a chemical property. Copper is a good conductor of electricity. Well, when you measure the conductivity of copper, it does not change into a different substance, and so that is a physical property. Ethanol is flammable. Well, if something is flammable, that means it catches on fire. And so for it to catch on fire, that is a chemical reaction. So this is a chemical property. All right, nickel 2 chloride hexahydrate is green. Well, to make the observation that it is green, it does not need to change into anything else. So that is a physical property. So that is a physical property. All right. So next, we want to look at intensive versus extensive properties. So intensive properties are independent of the amount of substance that is present. That means that whether you have 1 gram of it or 100 grams or 1,000 grams, then whatever that property is still going to be true. Whereas extensive properties depend on how much you have. So they depend on the amount of substance. Again, the best way to solve this is to go through and look at problem 1.3 on the in-class assignment. So I'll switch back over here to my document camera. And we're just going to look at each of these and determine, is it intensive? So determine whether it's an intensive or extensive. Again, intensive, it's independent of how much is there. So if you have 1 gram, 10 grams, 100 grams, 1,000 grams, it's going to have the same property. Extensive depends on how much is there. So the density of lead is 11.35 grams per cubic centimeter. Well, that is going to be true whether you have 1 gram of lead or 1,000 grams of lead. You're still going to get that same density. Since it's the same, that's going to be intensive. All right, so that is an intensive property. All right, the melting point of glucose is 146 degrees Celsius. So melting point, when something melts, it's still the same substance. So it's still the same substance. That means what? It's a physical property. But that's not what we're doing. We want intensive versus extensive. So intensive, that means if it's intensive, then the melting point of 1 gram would be 146. The melting point of 10 grams would be 146. And the melting point of 1,000 grams would be 146. Well, that's true. So that is an intensive property. The volume of a sample of benzene is 155 milliliters. All right, well, if we were to change the amount of substance, we would have a different volume. So that one is extensive. All right, copper is a good conductor of electricity. Well, it turns out it's a good conductor of electricity, whether you have 1 gram or 100 grams or 1,000 grams, it doesn't really matter. So that one is intensive. Potassium reacts violently with water. So potassium reacts violently with water. So, well, if you take 1 gram of potassium and put it into water, it will react violently. If you take 10 grams, it will react violently. You'll just want to be further away. If you have 100 grams of potassium, you want to be really far away because that's going to be pretty exciting. So the fact that it reacts violently, that is intensive. All right. The mass of a piece of metal is 42 grams. Well, mass, by definition, is an extensive property. So that is extensive. And then copper to carbonate is a blue-green color. So copper to carbonate, is blue-green. Well, it's blue-green whether you have 1 gram of it or 10 grams or 1,000 grams. So that also is going to be an intensive property. Now, I picked copper to carbonate. It's that distinctive blue-green color of the Statue of Liberty. So when you see the Statue of Liberty, that blue-green color that you see is actually the outside layer of the Statue of Liberty. The statue itself is made up of pieces of copper plate. When that copper oxidizes gradually, it forms some copper oxide, and then that copper 2 oxide to be specific, and that copper 2 oxide reacts with carbon dioxide in the atmosphere, and it turns to that blue-green color, that patina that you see on all copper statues and bronze and such. So it is a distinctive color. When they first built that Statue of Liberty, it was just copper. It didn't have that blue-green color to it yet. That must have been quite a sight to see. So, all right. So we want to go back. We want to go back to the presentation. And we want to look at changes of matter. So we've got physical changes, and physical changes are simply where matter changes, but it doesn't change into another substance. And so, for example, melting is a physical change. Melting point is a physical property, but melting itself is a physical change. Boiling is a physical change. Boiling point is a physical property. So properties usually describe changes. They don't always describe changes, but they often can. Chemical changes are when the substance gets converted into another substance. You get new bonds. You break bonds and make new bonds. And so it results in new substances, and we also give that the name chemical reactions. Well, we're going to spend a lot of time talking about chemical reactions. Turns out that's a really important component of learning chemistry. So we'll start with this particular chemical reaction. And when we're looking at this chemical reaction, we will find that here we've got copper, and it reacts with nitric acid to give us copper 2 nitrate, which we'll talk about how we name that stuff at a later point. A gas, which is this brown gas, nitrogen dioxide, and some water. And so I did this experiment in the hood. You don't want to do this like in your house because the brown gas that comes off, that nitrogen dioxide, is quite dangerous. And you don't want to breathe that material. So I've got this video already queued up on another screen. So I'm going to flip over to that video and I'm going to play that video. All right, so here is a penny, and pennies made before 1982 were almost all copper. And then I dispense some nitric acid into it, and you'll see the nitric acid is colorless, but as soon as that nitric acid starts reacting with the copper in the penny, you'll start to see some of that blue-green color, and that's copper nitrate. And you'll see the brown gas that is coming off. That is brown gas that is coming off is nitrogen dioxide, very dangerous gas. Which is why I did this in a hood. All right, well, that reactions mostly died down. In case you're curious, the penny survived after I was done with this. I think I pulled the penny out. It was shiny, but it was still a penny. Only a tiny layer of the copper was actually converted into copper to sulfate. And I did check, and I did not violate any federal laws by doing this. Sometimes people will tell me that I have somehow violated some horrible laws. In any case, that is a chemical reaction. Often you'll see color changes, not always, but often you will. You'll sometimes see gases that are produced, any number of different properties, but that is a chemical reaction. All right. Next, if you've got a combination of more than one substance, you can separate that. If they have different boiling points, you can separate that using distillation. So here we've got some salt water, and if we heat up the salt water, so here we've got salt water, we heat it up with a Bunsen burner. We will convert the water into the gas phase. Water has a boiling point of 100 degrees Celsius. Salt has a much higher boiling point, so we'll find that the water molecules will go into the vapor phase, but the salt molecules will mostly stay down here. So you can get essentially pure water over here. If you're looking at, hey, could we do this to produce water? This would be a very inefficient way to produce drinking water. So not something that we would want to do, but for drinking water purposes. But if you're trying to get really pure water, distilling is a great way to do it. Another type of separation technique that we have is called filtration. And when we filter something, we separate a solid from a liquid by pouring that mixture, that heterogeneous mixture, through a piece of filter paper. The liquid will go through the filter paper and the solid will stay on the filter paper. Filter paper is essentially like a coffee filter. We have another separation technique that we call chromatography. And chromatography will separate mixtures based on a difference in solubility in a solvent. And so here we've got just a mark that comes from a pen. The black ink in the pen is made up of several different compounds. And what happens is that the liquid will wet this piece of paper, and that liquid, the solvent, will kind of gradually work its way up. And as it does, some of the compounds in this are going to be more soluble in the solvent and some will be less soluble. The more soluble ones will move along with the solvent, while the less soluble ones will stay closer to the origin point. And so as time goes on, you'll see that you get a separation of the different components. Now, I've got a video. This is not one that I did, but one that Pearson did, and they did it a long time ago, so it's not a very high resolution video, but we are going to watch it anyway. here we go. And I'm going to click on play. So again, not a great video, but here we go.
In this paper chromatography experiment, the solvent ethanol and water, 1:1 by volume, is poured into a graduated cylinder. A black line is drawn with a felt-tipped pen across the bottom of a strip of absorbent filter paper. The paper is suspended in the mixture of ethanol and water. As the solvent is drawn up the paper, it carries the ink with it. The ink begins to separate into colored bands. With the passage of time, colors can be seen corresponding to different compounds in the ink. We have a red, a yellow, and a blue component, originally mixed to make the black ink.
All right, well, that is an example of paper chromatography, and there are many different types of chromatography. And chromatography is one of the most commonly used analytical techniques. There's gas chromatography, high performance liquid chromatography, just regular liquid chromatography, but they all depend on differences in solubility between a mobile phase and a stationary phase. And so we'll talk more about chromatography in later classes. Well, I'm going to stop the video at this point. I like to keep the videos under an hour if at all possible. So I'm going to stop the video, and then the next video will start on the next section of the book.